This is crystal field theory. In short form, it is called CFT. Already we have done valence bond theory, and by applying valence bond theory, you can find out the type of hybridization of the metal, and based on the type of hybridization, you can find out the structure and magnetic property of the complex. But CFT, this is one of the theory which is the modification of valence bond theory. According to this crystal field theory, as you know, in complexes, metal exists as positively charged. In maximum complexes, metal exists as positive ion, and maximum of ligands are negatively charged. So when the bond is formed between the positive metal ion and the negative ligand, between positive and negative ligand, the bond will form, that is not the dative bond, that will be ionic bond. I mean, due to electrostatic force of attraction between the positive charge and negative charge, they will form ionic bond. So according to crystal field theory, when the metal produce the bond with the ligand, since metal are positively charged, ligands are negatively charged, that is why due to this electrostatic force of attraction, they will form ionic bond. So these are not dative bond. According to CFT, these are ionic bond. Secondly, suppose your ligand is neutral ligand, because you know there are so many ligand like water and ammonia. These are neutral ligand. If the ligand is neutral, then also it becomes ionic. How? Because since these are polar molecule, the negative end of the ligand attract towards the positive charge of the metal. Ultimately, they also occur the electrostatic force of attraction. So according to CFT, according to crystal field theory, the bond present between the metal and ligand are ionic bond. And why the theory is called crystal field theory? Since metals are positive, ligands are negative, actually they form a field like electric field. They will form a positive your crystal field, and that's why the theory is called crystal field theory. This is positive field, this is negative field. So between this positive and negative field, you will get the bond, and that's why the theory is called crystal field theory. Secondly, when the ligand comes towards the metal, according to CFT, when the ligand comes towards the metal always, the ligand always come with a direction like this, As you know, metal contains some d orbital. There are 5 d orbitals. One is called dxy, one is called dyz, one is called dzx, one is called dx square minus y square, and one is called dz square. These are the d orbitals. If the metal contains 3d orbital, it is called 3dxy, 3dyz, 3dzx, 3dx square minus y square, and 3dz square. So these are the 5 d orbitals present inside the d subshell. Now these orbitals, they have equal in their energy, and that's why these orbitals are called degenerate orbital. Degenerate orbital means they have equal in their energy. But when the ligand comes towards the metal, then this degeneracy of the orbital gets split. I mean, the degeneracy of the orbitals will break. And how it will break? If it is a spherical field, then the degeneracy of the d orbitals will be maintained. But since the ligand comes with a direction, from all the corners the ligand will come, that's why the degeneracy of the d orbitals are undergo splitting. Some orbitals among these 5, some orbital will have lower energy when the ligand comes, and some d orbital of these 5 have higher energy. I mean, the d orbital undergo splitting. Now, before doing this, you should know about the shape of this orbital. The dxy orbital, this is x-axis, this is y-axis. Its shape is like this. This is called dxy orbital. Lobes are present in between the axis. Yz, the shape of yz orbital, this is dyz. Lobes are present in between y-axis and z-axis. Zx, the lobes are present between x-axis and z-axis. Dx square minus y square, first time you draw x-axis and y-axis. The lobes are present on the axis. in d x square minus y square. This is d yz. And in dz square, suppose this is z axis, it will be like this. This is called dz square. Now you have seen these are the 5 d orbitals. They have equal in their energy, but if you notice their shape, if you notice their structure, these 3 orbital, their lobes are in between the axis, and these 2 orbital, their lobes are on the axis, and that is why they are structurally different. And due to this difference in structure, suppose there is a complex like this COH2O whole 6 3 plus hexaaqua cobalt 3 ion. This is one of the octahedral complex because coordination number is 6. In this type of octahedral complex, when the ligand comes towards the metal, when the water comes towards the metal, then the metal will come towards the metal through the axis like this. Their direction towards the metal is through the axis, and since they come through the axis, that is why here lobes are on the axis now. That's why the repulsion will take place in this orbital and in this orbital. But here, since the ligand comes towards the axis but lobes are not present in the axis, that's why in this 3 orbital there will be no repulsion when the ligand comes towards the metal. So in these 2 orbital, repulsion takes place, and due to this repulsion, these 2 orbital will have higher energy and these 3 orbital will have lower energy, and that is called the splitting of degeneracy. Actually, initially their energies are same, but when the ligand comes towards the metal, the degeneracy is split into 2 series. These 3 orbital dxy, dyz, zx, this is dzx, these 3 orbital are called T2z series. They are commonly called T2z series, and these 2 orbital are called EZ series. I mean, EZ set will have higher energy, T2Z set have lower energy in case of octahedral complex. This is applicable only for octahedral complex because only in octahedral complex the ligand comes through the axis. So that is why if you want to draw for octahedral complex, I mean if you want to draw CFT for octahedral complex, CFT for octahedral complex, so these are the 5 d orbitals which have equal in their energy. These are dxy, dyz, dzx, dx square minus y square and dz square, and they have equal in their energy. Now when the ligand comes towards the metal, then this degeneracy is split into 2 series. One have more energy, here you will get 2 orbitals, that is dx square minus y square and dz square, and these 3 have lower energy because there is no repulsion in this 3 orbital. These are dxy, dyz, dzx. So like this way the orbitals get split into 2 series. This intermediate center, this is called Berry center. This is called Berry center. And the energy difference, this series is called T2z series and this series is called EZ series. I mean dxy, dyz, dzx, that series is called EZ, and the x square minus y square dz square is called T2z series. And the energy difference between these 2 sets of orbitals, that is represented by delta O, and this delta O is also called CFSE, I mean crystal field stabilization energy. Here I have written O for octahedral complex. If the complex is tetrahedral, then you have to write delta T. So the difference between the 2 sets of d orbital, sorry, this is T2z, this is EZ. The energy difference between the 2 sets of d orbitals are called crystal field stabilization energy, which is represented by CFSE. Thank you.